ray tracing, all these kind of analysis you can go with SBR plus. Okay, and this also can be used with antenna placement also. Okay, so and then the last one is if you are creating into an array of structures, like if you are going for array of structures or creation of array, at that particular time domain decomposition will be going. Okay, so and kind of if you are going for a bigger size of problem, this domain decomposition solver only distributes the problem into various cores. How that should be solved? Let's suppose if you are using an HPC, how much it should be distributed to each course, this will be defining this domain decomposition method. Okay, so
we need a good workstation or multiple computers to do this.
So this is all about the, let's suppose I can say solvers which is dependent on 5G technology. Basically we are mostly concentrated on 5G part in this. Other than that, we have characteristic mode solver and eigen mode solver and transient solver also available. We have now right now. Okay, so in this we will be defining the solution type here. Then the next thing is, it is common in all kind of simulation tools, creating geometry and assigning material property to it. Okay, so then we will be assigning excitation, the source point from where the source is going to be generated, that we will be assigning we will be creating a geometry and we will be assigning as a source point for in each and every model. And then the last thing is the boundary conditions. It depends upon again what kind of applications we are going for. Okay, so here we have different types of boundary conditions. I could say mostly as an antenna engineer we will be only aware of radiation or PML. Other than that, for array creation we have lattice pair. Mostly it is in all other tools, and in ANSYS also it was like master slave boundary condition. So that has been replaced as lattice pair boundary condition in ANSYS.
So previously it was like
it was master slave.
2021 master slave only.
Yeah.
Now they have changed or like.
Actually, in master slave we have to define like we will be choosing two phases. One is master and one is slave. But now what it is like, you don't need to define master or slave. Okay. Directly, what you will be doing here is you will be.
If you say one phase, they will
take oppositely like two if you are selecting two opposite X phases and you will be giving a lattice pair boundary condition. Then one will be set as automatically take it as master and other will be kind of a slave.
Okay, that automatically take the other surface.
We need not to define which one should be the master and which one should be the slave here. So that particular boundary condition is there. Other than that, I said I showed you this lumped RLC. That is also is a kind of a boundary condition which we keep it. And we have layered impedance. Okay, so this layered impedance is nothing but you can see this particular model here. So here you can see we had built an automatic driving assistance system simulation. This one is okay. So here we had made a road kind of a model here. So this is basically a layered impedance junction. Okay. So what this is a kind of a boundary condition which represents my road might be having n number of materials included in it. Okay. So for that each and every kind of layer will be included in that. So as a common, I will be using a layered impedance boundary condition, which will be representing a multi-composite of materials combined to it, and it will approximate material properties of it. Okay. So there are different kinds of boundary condition. You can, once you go here, you can see here like coupled, in that coupled only this lattice pair will be coming. Finite element is nothing but material. If you want to assign a material property like for 2D structures, whatever the copper traces, if you want to make, if you are not considering the thickness there, then we will go for finite conductivity or perfect T. Then if it is a perfect magnetic material, if you are going to use, we will go with perfect H. Then layered impedance. If for each and every, if you are not going for layered impedance, okay. If it is only a single kind of impedance which you want to compute, so for that we have impedance here. Fresnel, that is the Fresnel region which we have in the radiation field. Okay, in near field itself, we will be having the Fresnel field. To consider that particular region, if you are trying to place, like for an example, if you are emitting a radiation, if you are keeping some kind of object in Fresnel field, what will be kind of interpretation it will be happening there. So how we define a boundary condition for an air box, the same way whatever the analysis which I am making using Fresnel SBR plus, it will be giving out the outputs based on that Fresnel field effects, where the reactive components also will be a part of it.
At the same time, we can use all the boundaries.
Yeah, we can combine most of the boundaries.
You can add boundaries. You can add.
So these are different types of boundaries. Can say from here, these are after assigning boundaries. Like basically, you can use different sorts of boundaries are available based on your application. Like for an example, in a simple case of a patch antenna, it will be a radiation boundary condition, or else it is will maximum use a PML layer. And again, based on other things, we will be changing the other boundary conditions also here. Then the next one is solution setup. This is basically what is the center frequency and what will be the frequency sweep of from which frequency to which frequency we will be analyzing. All these set of parameters we will be assigning here, and with this we will be also assigning how my convergence should be. Okay, convergence in the sense how my meshing should be happening in my structure, that I will be assigning here. Okay, so based on that we have two factors. One is number of passes and maximum del S.
Okay, with adaptive.
Okay, so for adaptive meshing we have that option. What it will do is basically what adaptive meshing is nothing but you can see this particular condition here. To understand the computational background, it is pretty much simple. Don't go for too much deep into it. Just to understand it. So let's suppose this is the structure which we had made. Okay. So first thing is like based how the discretization is happening. Okay. It will discretize or it will make a big structure into smaller structures.
Pieces,
Okay. Smaller pieces. And what is the advantage of this particular adaptive mesh generation is nothing but based on the fields excited out. Okay. Where my field concentration is high, there my convergence or the structures which I am going to again discretize will be high based on the number of orders.
So it will automatically discretize, or like
it will automatically discretize. Like for an example, first
iteration it will run the entire thing.
Basic initial based on initial boundary condition, it will commonly discretize it. Okay, then next step what it will do is it will see, and wherever the field is getting distributed more on that particular mesh.
So it will automatically.
Like for an example, in this particular case, this is the mesh structure which I had made in the corner, and I had made some kind of mesh structure initially in this particular space. Here I don't have any kind of like field distributions happening here. So some smaller amount of field distribution based on the computation, like based on partial differential equation, how my field is getting distributed, that I'll approximate here. If there is a small amount of field distribution also, what this HFSS or CST also works on the same platform only. So what it does is it will concentrate much on that field radiated area. Okay, that's where the accuracy level of your result will be increasing.
The number of passes, if you are increasing, what happens?
That doesn't have nothing to do with the number of passes. The only data which is like
the del value we have.
Del S or the convergence rate which we say. It has to be very minimal in your case. Okay. So
what's the optimal value for the convergence? Maybe you can
not optimal value based on the structure. I will be saying you an example.
Because they are using 0.02, I guess. For
0.02 is normal.
Okay.
We don't have any. I'll explain you.
It's the default value.
Actually, convergence rate is nothing but how minute your structure is going to be. The last structure which is going to be built, how smaller that structure will be based on that particular smallest amount of structure, your field or the accuracy of your result will be more. Okay. So basically, let's suppose my convergence rate, if I keep it as 0.02, it doesn't mean nothing in this particular structure. But let's suppose if I need to consider this capacitive gap there. So that smallest amount of meshing structure should consider the gap between these two.
Okay.
Then only my capacitive effect, whatever it is happening there, or the electric field distribution, whatever it is happening there, that will be considered. If it is not considering this gap, then your C value will be changing. That C won't be constituting to your equation. Let's suppose F is equal to
But that how we can know, sir? Like it will take that capacitance.
Root of LC.
LC.
So that's what I'm saying. So let's suppose the same patch I'll take. Okay. So the same kind of H feed we'll take. So what it will happen is for general meshing, based on the maximum in patch antennas, the field will be generated on the edges maximum. So my meshing, you can see here, the meshing is more concentrated here. Okay. So then what it happens is, let's suppose you had made an 0 for 0.02. The meshing size is somewhat this large. Okay. So what it happens is, it is not considering the gap here. It should be kind of, the meshing grids should be very much confined in this particular area also. Okay. If it is 0.02, the meshing size is this much. So here the capacitance which has been generated is neglected.
Okay.
So what it happens is, the overall capacitance which it is there,
Okay.
it gets affected. Because of that, the frequency what it is there, it will be not accurate here.
Okay.
So what you have to do here is, once you compute it, once you give or once you run the simulation, go for plot mesh.
Plot mesh. Okay.
See the confined areas, this particular area, go deep into this and see is the meshing has been properly confined, or that particular capacitance gap or the smallest area has been considered or not.
So first we simulate the thing. And
Yeah,
then we
generally
go
you can
back.
simulate it with the default one.
Okay, default value.
Then,
And
go zoom in and see your meshing, how it has happened.
okay.
Based on meshing, decrease the, if it is considered, then leave it, or else go deep into your structure, see how much, again if it is 0.02, go for 0.002.
Okay. Okay, sir.
Then again the structure size will be reduced here. Okay, then you can see it, and then only you can approximate. Like tool has nothing to do with the accuracy rate.
Oh.
How we are analyzing the problem, that is the first thing. Okay, how we are approaching that is the first thing. The main part where we are lagging, like we say, like simulation result is not much accurate, or with the measured result it is not matching. This is the area where you will be facing the problem. Like you will be giving the default value of your structure. Like whatever the simulator, it will be having a default value of 0.02. But your structure might need to be refined till 0.002.
Okay. For filters, sir, the same problem occurs. If I am increasing the number of passes only, it is converging. Otherwise,
Sir, that's what, sir, I
there
will
is
say.
poor
There
convergence.
is one criteria. That's what the next point. The first point is, the convergence rate should be exactly matched. Okay. What other thing is, like, if you give this particular convergence rate very small, and number of passes is nothing but number of iterations or cycles it is going to be circulating again and again. So first iteration or number of pass, for example, let us say in 0th number of pass, the initial meshing will happen, and it will just see as like my convergence rate has attained or not. Okay. Then in first that is second number of pass, it will be confined bit more, and it will see whether this particular 0 point, for example, in my 0th number of pass, if it is 0.1, my convergence rate is whatever I had attained. Then in first number of pass, it will be around, let's suppose 0.01. Okay. But my target value is
0.02.
0.02. Let's suppose we had attained in around 0.15, and in third number of pass, it is 0.02, or it should be less than that. Okay, here what convergence rate means is, like, this target is the convergence rate which you are giving here.
Can we decrease that one?
So that is increasing at that time now?
Which, sir?
So first iteration and second iteration is
Yeah,
increasing.
it's decreasing.
Decimals.
0.01.
0.015. It's increasing number of that, and then
Okay.
0.05.
Let's suppose
0.05. I can say.
0.05.
0.05,
And 0.02.
something 0.025,
0.025.
something you can keep it. Like, it should be a decreasing decimal numbers. Okay. So what it does is, this is the target which I want to go for. If you are given 10 number of passes, what the simulator will do is, it will go for each number of pass, but it will see the target where it has achieved. In each and every cycle, it will concentrate on whether I had achieved the convergence rate or not.